Welcome to the 6.5 Summit. I'm Shelley Kramer, one of the founding partners of Futrim. And my team and I at Futrim and the team at Moor Insights and Strategy, we're really glad you're here. In this keynote session, we're going to hear from Raj Singh from Marvell Semiconductors. And Raj is going to talk with us today about technology, hardware and software technologies that are driving the new architectures, open platforms, and creative implementations in next-gen mobile infrastructure. I know that sounds like a mouthful, and you know what? It was. I can promise you, you're going to love what Raj has to say. Let's jump in.
Good morning, everyone. I hope you're all doing well and staying safe and healthy in these very uncertain and dangerous times. My name is Raj Singh, and I'm the EVP of the Process Business Group here at Marvell. For those of you who are unfamiliar with our company, Marvell is a fast-growing, innovative fabless semiconductor supplier focused exclusively on semiconductor solutions for the infrastructure market. This focus has allowed us to enable our customers to build truly differentiated radio networks and innovate within industry standards. Earlier this week, when I was thinking about this talk and what innovation means in the radio networks today, it occurred to me that perhaps this conversation would have been dramatically different if it had taken place only a few short months ago, prior to the advent of the COVID-19 pandemic. For a start, the event would have been in person and in real time, something that is not possible or unfortunately even practical at present. Why does this matter? If this is indeed the future, then many parts of the internet, networks, connectivity, storage, and security will have to morph and change to accommodate the largest work-from-home experiment that the world has ever seen in modern history. Of course, work from home is not new. Certainly in the US and other countries, we've been doing it for years. But the rate at which we've had to have people move away from their workplace, away from enterprise, from on-premises, from headquarters, from shops, from factories, into their homes, has been unprecedented. This chart clearly shows that there have been a rate of home workers, which seems to be in the 25 to 30% range, with peaks at Thanksgiving in the US or at year-end holidays as well in other parts of the country. What is different now is that since the beginning of this year, that rate has gone from 30% all the way up to 60%. And that is quite new. Let's talk about things morphing and change. Change is part of technology, it's also part of society. And what we find is that change has accelerated with each passing year. The last 50 years have seen amazing innovation in multiple parts of industry and in technology. But in the last 10 or 15 years, that rate of change has accelerated in unprecedented ways, particularly in wireless networks. If we look at the slide above before you now, you'll see at the turn of the century in the US, there was a lot of change going on. Electricity, the motor car, a lot of things, packaged goods, a lot of things that were unheard of in prior generations came to be. The rate of adoption was slow with early adopters earlier, but as prices fell and mass markets developed and bulk production became available, then things moved faster. Cars, trains, travel, electricity, the telephone, television, all followed certain curves, each successive curve being slightly faster than previous ones. Certain things like world wars accelerated certain changes and created new technologies, the space race in particular. But when we got to the last 15 years, we saw an unprecedented change in both function and the rate of adoption. The next slide I'm going to show you is an advertisement for Radio Shack, which was a ubiquitous part of American fabric in the 90s and 80s. And here's an ad for a bunch of stuff that was being manufactured, which no longer, neither the store exists nor many of the functions things. Answering machine. There are still people who have answering machines, but it's not a normal thing. Every single function on that advertisement in the newspaper is now available on your iPhone or your Android phone in your pocket, with possible exception, and I say possible exception, of the speakers. And that's quite remarkable. So all the manufacturers, the people who were doing those things, no longer are manufacturing those products in any volume, or they have become niche markets. That's a huge rate of change that affects both manufacturing, technology-based, and society. The wireless industry innovated first in voice and connectivity. Freedom of location and of movement ensued. Mobile phone manufacturers flourished, wireless operators were born, then innovation in text messages as 2G came online, and first generation video messaging appeared shortly thereafter with 3G. As this progressed, you could see the rate of adoption of technology increased with each successive generation. Lower handset prices, better services, affordable usage plans all contributed to the adoption rate. In 2G in particular, the availability of plentiful spectrum in a more or less a single band across the world for GSM allowed a proliferation of handsets that could operate across countries, something that was unheard of prior to the invention. The advent of 3G allowed voice, mobility, and for the first time data to become the new norm. Then came the advent of the iPhone. In 2007, when Apple introduced the iPhone, it literally had an effect that changed the wireless industry forever. For the first time, it combined multiple functions, as we saw in the ad before, into a single device operating on 3G, and the need for data became ubiquitous. No longer did people talk about the killer app for 3G. They talked about how to limit the amount of data running on the networks. This was a massive change in what happened. And the chart you're looking at now shows a bar chart of all the data and voice traffic prior to 2007 and the explosion beyond 2007 as people slowly got to the idea that mobile apps were going to take off and those apps were all going to consume data. Very quickly, data traffic overtook voice traffic, and of course this also meant that the kinds of networks operators were building, the kinds of equipment OEMs were producing was different and focused much more on data traffic, and the voice became something that was just a standby in any given network until you got to 4G. With 4G, you eventually had a relative flattening of the network that was IP based. It allowed significantly higher data rates, particularly as you were twinning pieces of spectrum together, and it allowed a new lease of life for many, many new applications and an explosion in what could be done with those applications. There are literally tens of thousands of applications running on LTE networks today that did not exist before 2007. 4G didn't just allow people to use data. It allows them to use large amounts of data, often at rates that were at par or lower than 3G rates. But it did one other thing. It created the premise in consumers that data was available as an always-on service. Broadband was always on no matter where they were. If they were in a desert, like this poor fellow here, then they could have broadband access. If they were in a forest, on the ocean, by the seaside, on vacation, the expectation became that they would have 4G connectivity and they would have ubiquitous broadband data. When we got to 5G, it was, of course, faster than 4G, had less latency than 4G, but it was different in a fundamental way. It was the first protocol standard coming from the 3GPP body that embodied in it not just parts of things beyond handsets and tablets, but large portions of what it would take to do industrial control, industrial automation, smart cities, true remote medicine, virtual gaming without console requirement, intelligent factories. All these use cases became an integral part of enabling 5G. Now let's talk about the real and tangible benefits of 5G. It isn't just about faster speeds, lower latencies, enhanced reliability, more capacity. All those things, of course, are true and welcome improvements to previous protocols. However, 5G also has a very crucial technology called network slicing. In network slicing, the operator can combine the assets inside the network to provide a unique and dedicated slice for a particular service or set of users. Think, for example, of first responders, for emergency crews, for ambulances, for police, firemen going to a particular event. They want guaranteed connectivity, they want guaranteed phone calls, and network slices allows the operator to dedicate a guaranteed amount of capacity and of resources to provide the services. Or people in the future watching a football game, wanting to have the latest scores, and there are 4,000 of them, you can set up a scenario where there's dedicated resource for that particular event to be managed. Providing latency efficiency for remote things like remote medicine, even remote surgery, where you cannot even allow an extra millisecond to creep into the quality of service. It must be a dedicated stream. Those can all be catered for through network slicing. Let's talk a little bit about spectrum. Spectrum is very valuable. It's also quite scarce. 100 years ago, there was very little spectrum being used for anything at all. Even 50 years ago, most of the spectrum was being used for military uses or for radio or TV. But today, there are a multitude, Wi-Fi, Bluetooth, multiple military and commercial applications that use a wide variety of spectrum. The last big spectrum worldwide allocation was, of course, GSM, and that was a single band for the most part, and that allowed large parts of the world to have seamless roaming on the network, and contributed significantly to the success of GSM networks. And in order to provide 5G with adequate spectrum, the industry has created a multitude of innovations, both in the sub-6 spectrums, sub-6 gigahertz spectrums, where there's the techniques needed are evolutionary from previous protocols, but more importantly, in previously unused spectrums, in millimeter wave, 28, 38, even at 60, where the industry has done enormous amounts of innovation with massive MIMO, with edge computing, with disaggregation of the radio network. Various governments enacted policies to allow access to sub-6 gigahertz spectrum, mandated deployments, and tied 5G to a host of infrastructure investments. And this is beginning to happen in the US, it's certainly happened in Asia, and we're seeing a boom in 5G deployments in certain countries. Not just for handsets, not just for tablets, but for a whole host of new industrial usage that could reap huge benefits for industries across the board. So if you look at network topologies, it's clear that there are certain trends going on. One trend is virtualization of higher layers. Another trend is pooling both of higher layers and of the baseband parts. Certainly more intelligence in the radio head. We're seeing standard COT servers being used in conjunction with dedicated cloud-native hardware to enable O-RAN type deployments. These are very innovative ideas, and it's certainly worth considering. We have worked very closely with a number of operators and our OEM partners to enable both O-RAN and Open RAN deployments. We're very happy to be able to do that. Traditional deployments still carry on unabated. CPRI is gradually getting replaced by eCPRI. Radio heads becoming much more prevalent in the massive MIMO space, more intelligence than radio heads, as I said earlier. And then lastly, more and more attention being paid to edge computing, where decisions are being made autonomously from the core of the network, and less traffic and decision making is being burdened on the core itself. And as you'll see from this diagram on the right, there's a traditional split 8 deployment where the entirety of the L1, L2, perhaps even part of the L3 is located in a single rack for a DU. And typically the front haul for this has been CPRI or some version of CPRI appropriate for the OEM. But as time has progressed, of course, with the advent of radio or Ethernet, or eCPRI, Ethernet protocols on the front haul, particularly for 5G where the data rates are so immense, have also meant that more of the lower L1 functionality for the PHY has migrated to the radio head. 7.2 split is a great example of that. It's the official O-RAN split, and that clearly demonstrates this very well. And then 7.3, which is the next step from that, which is sort of OEM specific, and different people have taken a different approach of how to do that. We're working with several OEMs on that as well. And then the small cell forum, for sort of obvious reasons, in all-in-one type scenarios, have also introduced the split 6, which takes much more of the intelligence into the radio head. All of these are valid. All of these will require new topologies, new silicon, new innovations for each use case that has to be deployed and tried. Now we talked a little bit about innovation and how 5G is driving innovation, but how use cases and more intelligence in the radio head. What does that all mean? What about AI and ML? And how does that all fit in? Well, it turns out that you can do an awful lot with AI and ML as long as you're doing things inline. You can do offline too, but a look-aside model is more problematic for that, and it's our belief that using AI in the RAN is a great idea. Using AI and ML in the radio network is a unique and really great opportunity for the industry. Starting from the radio head, where you can use it to deal with problems of nonlinearity, going to this DU, where you can talk about interference mitigation and other techniques, all the way to looking at interesting and innovative ways of scheduling things, and also for improving the channel performance in the network. These are real-world problems that typically are solved by huge amounts of either software or hardware effort to get good results. But with AI, particularly with good training models, and those will obviously evolve and get better over time, you can easily see a way over time to use that to be much more efficient in the radio network. We talked earlier about the advent of massive MIMO radio heads, and this is a great innovation which started off as a fairly niche product, but as costs have come down, as silicon has got more efficient, as transceivers have got more integrated, the cost of massive MIMO radio heads continues to come down, and the benefits of doing that, the total cost of ownership, particularly in terms of installation and maintenance, is significantly less than traditional 2x2 or 4x4 radio heads. And what we're seeing is massive MIMO radio heads in conjunction with beamforming offer huge advantages in 5G for capacity, for throughput, and we see a number of people, both not in the operator world and in the OEM world, beginning to deploy those at scale. From a very single-digit percentage of radio heads shipped in the world for massive MIMO, we expect them to be in the large double-digit numbers very quickly, and we're seeing that in certain countries in excess of 60 or 70%. In one particular country that we know of, the number is in excess of 80%, mostly because the cost of labor is so high, it easily justifies the TCO. And finally, I'm going to touch on edge compute. Everybody talks about the edge. There's the near edge, there's the far edge. What does it really mean? In order for the RAN to operate efficiently, of course, it needs the radio head, it needs the distributed unit, it needs the central unit, and it needs to be able to send data up the stack and then down the stack, and you have to make intelligent decisions how that data is handled. If you think about it, if you want a 1 millisecond response time in 5G, you can't possibly be sending the electrons thousands of miles away to be acted on to bring back. So you have to start building more and more intelligence closer and closer to where the decisions have to be made. So you start seeing scenarios where large-scale deployment of not just local offices, but also intelligence at the edge, which is allowing autonomous decisions, perhaps in conjunction with the AI/ML, for large parts of the RAN network that are then communicated across a broader orchestration fabric to other parts of the network or other. This could allow huge amounts of innovation, not just in traditional SONs, but in true self-healing and self-managing networks for the future. That pretty much concludes my talk here today, and I hope you enjoyed that. Certainly helped presenting to you. However, I have a short video on the capabilities of MIMO, which I will leave you with, and I will see you in the next session.
Data infrastructure has never been more critical to the global economy. It's what keeps the world connected, businesses running, and information flowing. At Marvell, we believe that infrastructure powers progress. Trusted by the world's leading technology companies for over 25 years, we move, store, process, and secure the world's data with semiconductor solutions designed for our customers' current needs and future ambitions. We're changing the way tomorrow's enterprise, cloud, automotive, and carrier architectures transform for the better. We're driven by the belief that how we do things matters just as much as what we do. That's why at Marvell, we go all in with you. Because with a foundation built on partnership, anything is possible. Marvell is essential technology done right.